Everybody have coffee, stay warm, right? That's the first requirement. And then the second thing is you actually have to find a seat. So thank you very much for coming. I appreciate it. My name is Jeff Layton. I'm from AWS. I'm in what we call our scientific computing team, or as we like to call ourselves after dinner, the psychos. I must apologize. I inadvertently left off my co-presenter, Dr. Spenzuris. Close enough, from Fermilabs, and he's going to come up and speak as well about what Fermilab has been doing in the cloud. We have a mic in the center. If you have questions, raise your hand, scream out, Jeff, hey, hey. I can't see real well, but I'll try my best to find your hand and answer your questions as we go. Otherwise, let's get started. Here's the agenda. I'm going to talk about why we're using cloud for HPC and what customers have told us why they've come to Amazon. I have no idea why it does that, but it does. Some of the tools. I'm going to talk about Spot and HPC, and since I live in the South, if you remember some of the phrases, Southern phrases, it's like peas and carrots. And then Dr. Panzuris is going to come up. I have a demo. It's not working really well here. I keep getting dropped off the internet. But I have some screenshots to show you some of the demos of the tool. And then I'm going to finish with a summary. If you have any detailed questions, glad to talk about them. But that's probably something we should probably take offline. But otherwise, I'm open for anything. These are the primary reasons that people tell us that they use AWS Cloud for HPC. First is scalability. If you need a lot of cores, you just start them up and you use them. If you don't need them, you turn them off and you don't pay for them. They really like that feature. Another one is time to research. Normally for on-premise clusters, you have to go through a process. You have to send out RFP requests, get them back, review them, blah. You've probably been through this routine, and it takes months. But with the cloud, if you have an idea, immediately you can create a cluster, run your application, see if it works or if it doesn't. Sometimes we call this failing fast. But really, for us, it's time to science, getting things done as quickly as you can. And it keeps changing on me. Worldwide collaboration. And I'm going to talk about this a little bit more because some new tools that have come into the cloud really help with worldwide collaboration. You get to work with the latest instance types and latest technology. And I actually had a customer send me an email and said, I almost cried when I could switch from a C4 extra large to a C4 8 extra large. A true geek for you, just near and dear to my heart. And of course, you can always save lots of money depending upon how you run your application. And the big subject of this presentation is rather than drag cables under the floor, put in seismic trays for the cabinets and do all the cable labeling. I hate cable labeling. Rather than do all that, all you do is write a little code or actually run an application that creates the cluster for you. Infinitely easier. And if you need to reconfigure, you just change the code. Rather than have to drag cables around, change the cable labels. It's a nightmare. We typically think of 4 phases of getting into the cloud for HPC. The first phase this is typically where everybody starts, is what we call Forklift. I want to make the cluster in the cloud look exactly like my on-premise cluster. Everybody's used to it, so they're very comfortable with it. The second stage is start to port to the cloud, to adapt to the cloud. Things like auto-scaling, or using Spot instances rather than on-demand instances. The third example is what we call born in the cloud, and a classic example of this is Cycle Computing's tools for getting into the cloud. And then the fourth level, I guess this is nirvana, is rethinking your application. And we're starting to see people do this. This is looking at things like microservices or Lambda, rather than classic HPC applications that maybe use MPI or Fortran or C. So I'm going to show you a couple quick examples of what I mean by Forklift. So everybody's pretty much used to what an on-premise cluster looks like. You have a bunch of compute nodes and a master node. with some kind of interconnect, Ethernet, InfiniBand, whatever it is, and some kind of storage, NFS, parallel. So this is the classic on-premise cluster architecture. We can do the same thing in the cloud, no different. This is the forklift. But instead of calling them nodes, we call them instances because they're virtual, but you can create the exact same architecture. The next step is to adapt to the cloud. And this is where we do things like, I need more nodes. You start them up, you're done with them, you turn them off. That is almost impossible to do with on-premise. You can do it, but it's really, really difficult. These are the two levels that we see HPC users take advantage of the AWS cloud. Some of the tools that you can use. This is just a quick list, and then I'm going to talk about the last one. The first one is MIT Star Cluster. So if you're just getting started and you Google AWS HPC tool, this is probably going to come up. It was developed a number of years ago. It's really no longer being developed nor supported, so it's probably not the best place to start. If you're already a Star Cluster user, great, keep going. But there are some people developing it, but they're keeping it internal. They're not sending it out to the world. If you already have an existing on-premise cluster and want to do hybrid, where you burst to the cloud, Bright Cluster Manager is one of the best tools, if not the best tool for doing that. So you use Bright Cluster Manager for your on-premise cluster, and it will then burst to the cloud for you. The third one is, and by the way, Bright Cluster Manager is commercial. I don't want to represent that it's open source. Star Cluster is open source. Clemson University started a tool named Cloudy Cluster, and one of their companies, local companies, Omnibond, has commercialized it, providing support. Boy, I must be talking way too slow. It is also commercial, and it's available in the AWS Marketplace. Another tool that is open source that was developed at Amazon called CFN Cluster. This is a great tool for learning how to get started to write your own code to create a cluster in the cloud. So if you want to write a tool or something that builds up your own HPC cluster, CFN Cluster is a great place to start. We recently had a new tool added to the AWS Marketplace from a company in the UK named Alsys, and it's called Alsys Flight. It's on the marketplace. It costs you $0, besides what you have to, you get charged for the AWS infrastructure. They don't charge anything for their software. I'm going to talk about it a little bit more in depth. I'm getting too excited. But it gives you a complete cluster with a set of tools and over 750 applications already pre-built for you. This is Alsys Flight. So it looks like a typical, what you would see if you have an on-premise cluster or a national supercomputing center. On the left-hand side, you're going to see the typical login command line. And Alsys is, let's see, I think that's Latin for moose. So you can kind of see their moose logo there. But it comes with environment modules. It comes with a job scheduler. It comes with a set of tools from Alsys to install these applications. And on the right-hand side, you can see that you can spin up a GUI really quickly in your cluster. So on-premise cluster, you usually have to copy your data out, bring it back to your desktop. I knew it was going to do that on me. Bring it back to your desktop or to some visualization node to visualize it. Alsys Flight allows you to then just immediately start a VNC server and link to it, and you can share that link with collaborators around the world, and automatically you're visualizing data. And I'm going to talk about that a little bit more. This example is just ParaView. It's just a simple OpenFOAM example, CFD example, showing that you can visualize the data right off the cluster. As I mentioned, it has pretty much the same tools as virtually all HPC systems, so it has environment modules. If you're used to that, if your users can handle that. It does use SGE Sun Grid Engine as the job scheduler. So you still have to write some scripts, and we'll talk about why we're going to use a job scheduler in the cloud, because basically the cloud gets rid of job schedulers. There's some good options for using them. I'll talk about those. It has over 750 applications. I think I checked 2 weeks ago, it was over 800, and they keep adding them. If you don't see one that you like or need, send them an email. There's a community board where you can post and say, how about version 4.1 of Octave? And they'll see what they can do. If you subscribe to their support, they'll do it immediately. This is a wonderful thing about Alsys. Their tool is called Gridware. You can see it in the third bullet. So they have that's what you use to install the applications and uninstall them. So it's really pretty easy. Alsys, Gridware, install R. And I'll show you that in the demo. Alsys, Gridware, search. And that's what you can use to look for applications. By default, it uses the spot market, except for the master node. That's on demand. But by default, it uses spot instances for all the compute. You can choose to use spot instances. There is a way to make it on demand if you're more comfortable with that, or your application's not quite ready for spot. It does do auto-scaling based on the queue length. So if you have a number of jobs that have been queued, it's going to look at how many are sitting there waiting for resources, and it's going to spin up nodes, instances, for those applications to run. Of course, within limits. I mean, it's not going to go crazy. You don't want 10,000 things spinning up just because someone made a mistake in a job script. But it will look at that, spin up instances that are needed. It will then wait to the nearest hour, right? Because AWS bills in terms of hours. It will wait to the next hour, and about 5 minutes before, it'll turn off the nodes. So then you stop paying for them. So they're there if you need them, and if you don't need them, they're automatically turned off. This is an example on the right-hand side. This was one of our Psycho members is a genomics expert, Mia Champion. I'm not sure if Mia's around. She can talk a little bit more about this, but there's the, she is here? Yeah, in the exhibition hall. Okay, yeah, so we'll talk about that a little bit too. There's a tool called the IGV, Integrative Genomics Viewer. This allows you to look at two genome sequences and compare them. You know, you're looking for variants, things that maybe cause disease. So what she did is she had a friend in Europe, and they pulled up two genomes with the IGV, and they were able to walk through the genomes looking for the variants. One person in Europe, one person in the US at the same time. It's all done through, if you've got VNC, so if you've got a Mac, Windows, you're fine. If you've got a Linux box, you're fine. I don't think there's an OS that doesn't run VNC. So this is one of the really cool things about Alsys Flight. You immediately get a Vis Tool. Any questions about some of the basic tools? If I can see, there we go. Okay, so let's talk about Spot and HPC, which, like I said, is peas and carrots. Anybody know the reference for peas and carrots? Forrest Gump? That's where most people have heard it. But living in the South, I hear peas and carrots all the time. So let's go ahead and talk about that. If you're not familiar with Amazon, we have 3 pricing models for paying for your compute. The compute is the same. All you're doing is paying for it in a different way. So we have the classic on-demand instances on the left-hand side. This is what you think of when you say, create instance when you're in the console. We also have the option of reserved instances. These are for workloads that you know are going to be fairly constant over time, and you pay some upfront costs, and that will greatly reduce your costs later on. And then, of course, we have the spot market. So at Amazon, we look at what people have reserved, what people are typically using, so we have that amount of capacity, but we keep some extra capacity around because people may want more, or we may have new users. So capacity may not be used at that particular time. We make that available to users at a much reduced cost through what's called the spot market. So you bid for the instance. So you're not going to bid maybe the full price, of course, but you may bid something a lot lower. If your bid's accepted, you get the instance, it's started up for you, and you have access to it. If your bid price is exceeded, the instance is taken away from you. You get 120 seconds, 2 minutes notice, but it's taken from you and given to the person with the higher bid. But believe it or not, the market is not that dynamic. We check it about every 15 minutes, and the market's pretty stable, except around Black Friday, Cyber Monday. That's when I would just stay off, wait a few days until they're finished. Then we can get back to it. So the spot market is a great way to save a lot of money. We publish up to 80 to 90% savings as kind of our target. You're not guaranteed that all the time, but that's what we typically see. And this diagram shows it a little bit better. Some people call it a market filler or a spot filler. So this is where the opportunity is for running HPC codes. Even though they may get interrupted, you can get the instance taken back from you within 120 seconds. But let's say your application is 120 seconds notice, I'm sorry. But let's say your application is almost done and it fails. Just rerun it. It may be a fourth of the cost already, so why not run it again? You're still saving money. It may take you a little extra time, but you can save quite a bit of money. This just shows you an example that I cooked up around, I think I did this one in March. So I looked at the most expensive spot that I could find versus the least expensive on demand. Okay? I did it in US East on the left-hand side, 4 compute nodes, master node, and I ran it for 2 hours. Spot was about a third of the cost. It was never interrupted. On the right-hand side, I did 16 compute nodes, 32 hours, and again, I did on-demand in the East, because that was the least expensive, and Spot in US West 1, California, was the most expensive at that time, and it was a fifth of the cost. Spot and HPC love each other, it's peas and carrots. This is a great way to save money or run more applications. I think I'm going to stop there. Spence, you want to come on up? He's going to talk about the Fermi National Lab and what they've been doing with HPC in the cloud. I think it's going to be really interesting. Oh, got a question. I saw a hand.
Computing as defined in the National Security or the National Strategic Computing Initiative sponsored by the White House.
So the question was, what is our involvement, I guess, with the Exascale Computing Initiative from the White House? We actually have several people that have talked to Congress and talked to the White House about that. Beyond that, I'm not sure that I don't know of any interactions, but I'll check for you. I'll check on that.
And then one last question. What's your feeling about Moore's Law and the ability to support these number of clouds and processing? Because between myself and my compatriots, I mean, we have a pretty lively discussion about whether Moore's Law is going to continue in the future or not. So just your personal.
Okay, so this is personal. So I'm taking off my AWS hat and I'm putting on my Jeff Layton propeller hat. I think Moore's Law is probably going to end. I can't tell you when. But there's new architectures that we can use to improve performance. So for example, I don't know if International Supercomputing Conference is going on. The #1 machine was just announced today. It's in China. Whole new chip architecture. No caches. And 260 CPUs per node. So I think there's other ways to skin the cat in terms of getting more performance. So anyway, that's my personal opinion. So, I'm sorry, Spence.
Oh, no problem. So how do we advance here, or
Just the big green button.
the big green? Oh,
The
very
red
good.
one goes back.
All right. So I will actually discuss how we've partnered with AWS, starting with high throughput computing, which we've actually done a lot of work, and then I will discuss how we plan to continue with high performance computing. Regarding Moore's Law, which will end, and the new architectures that Jeff mentioned, the tricky part with the new architectures is to actually evolve or modernize your applications to take advantage or to be able to utilize said applications, because your applications the way they are will have performance issues. But that's a different talk and a different discussion. So as I said, I will discuss how we partner with AWS, but first of all, I should introduce Fermilab to you, because I'm certain that you're not very much aware. So Fermilab is America's premier particle physics and accelerator laboratory with a mission to solve the mysteries of matter, energy, and space-time. And our users, if you wish, are on the order of 4,500 scientists all over the world. So it is a pretty big user base, an expert user base, and non-local user base. And these guys use both our accelerators, our detectors, and our computing. So what science do we do with these accelerators? So we utilize high-energy particle beam collisions to discover the origin of mass, the nature of dark matter, and extra dimensions. Cool stuff, I guess. We also employ high-flux beams to explore neutrino interactions to answer questions about the origins of the universe, matter-antimatter asymmetry, and force unification. And finally, again, we use high-flux beams to explore air processes to open a doorway to realms to ultra-high energies close to the unification scale. Which, again, in order to understand big science, what you need to do, at least in this field, is try to get as close as possible to the Big Bang, to the origin of everything. You want to get your energies and you're going to get your interactions to explore physics that are way beyond the scales of everyday life, of today's world. Anyway, just to give you an idea on what these experiments do, what our research does, and I don't have a pointer, so I'll use, well, anyway, on the left, I do have a pointer. Right there. My apologies, I do have a pointer. So let's look at the plot on the left. So I have two examples. On the left is neutrino experiments, and on the right is high energy experiments. We use neutrino experiments, we utilize high flux beams. So Fermilab is in Batavia, Illinois, just outside Chicago. It sends neutrino beams to two experiments in Minnesota, Nova and Minos, and it will send, we're working on it, even farther away, a beam to South Dakota for the Nova detector. Now, I'm sorry, for the Dune detector. The Nova detector, which is the farthest away, if you wish, in Minnesota, is 14 kilotons of liquid scintillator that when it's exposed to the beam, it looks like that. It's lit like a Christmas tree. So there's a lot of data in its event. I'll come back to that. On the right, you see the 27-kilometer circumference of the $10 billion accelerator at CERN, which is in Switzerland. And the experiments that run here are responsible for the discovery of the Higgs particle, which, if you follow science, you would have read about it a couple of years ago. So Fermilab participates in one of these two experiments, and we have one of the biggest computing centers that provides resources to analyze these events. So since I mentioned massive detectors that produce massive data, how massive is this data? Let's look at Wired magazine. It's a little bit old, it's 2013. But if you look at the size of the total data set of one LHC experiment, it is comparable to the content uploaded to Facebook each year. It's bigger than the Google search index. And this data is getting bigger and bigger every year because the detectors are getting better and the accelerators are getting better. And to make things even worse, this data that you saw in this picture, this big box full of tracks, they start in as the most elementary objects. They are instrument data that they have to be reconstructed to physics objects, and then they have to be analyzed to find physics patterns that are relevant to the event, to the physics that we want to discover. And to make things even worse, if that is an expression, the way that scientists analyze this data is highly non-canonical. It comes in spurts. It comes in spurts because of physics conferences. It comes in spurts because of rumors that something is to be discovered. So it's not steady state. So provisioning for this thing is difficult. So since provisioning for this thing is difficult, elasticity is very, very important. So we started at Fermilab for the last year to evolve the concept of HPC cloud. So this concept, it means to provide cost-effective and efficient elastic resource deployment, utilizing a sophisticated decision engine and middleware for automation. A single portal to heterogeneous computing and storage resources, both local and rental, both commercial and academic. And, oops, it did it to me too. It's not just you. And of course, since we're talking about clouds, commercial clouds, initial focus on commercial and enters AWS. And we have a partnership that is now, I think, close to a year. And that has been very, very successful. On the right here, you see it's just a cartoon of the architecture of this thing. I'll come back to it, and I think I should give Jeff a chance to do his demo, so I'll move quickly. So AWS infrastructure has been very, very well matched to what we want to do. what we're doing actually with HEP Cloud. Because AWS Cloud Formation automates the setup and tear down of a bunch of things. I realize that I'm too technical here from the level. So in any case, we have all the tools necessary to do what you need to do in order to have this elastic deployment in the most seamless possible way. We don't really need to bother with the details here. It's taken care of us by the toolkit provided. And I have an example here, but most likely it's too detailed. So everybody, of course, should appreciate that the success of the workflow depends on the availability of the software services in the running environment. And automating the deployment of such services on AWS on demand has been, it's been very important for us because both enable scalability and promotes cost savings. And services that include data caching, for example, squids, submission service, data transfers, etc. And all services are made deployable on demand. Down here I have an example of an on-demand squid. Again, if you are familiar with the technical stuff, this is trivial. If you're not, it's not important. So how does it all work? Before I show you some actual examples, let me drill down a little bit to the heart of the architecture of what it is HEP Cloud business, and why the cloud part is very important, and how the HPC part might become even more relevant. So in any case, bottom line is any workflow coming in, we'll call it job here, it doesn't matter, comes with a manifest. This manifest contains a description of the requirements of this workflow, of what kind of resources it needs, what kind of data it will move, and so forth. The algorithms that are running in the decision engine are aware of the available resources, are also aware of environment and capabilities such as networking, pricing, as far as cloud is concerned, type of resources, and so forth. So this thing comes in, checks if there is availability on on-premise resources. If not, sets up a commercial cloud, unless this job came in and it said, do not run on it. I don't want to spend money. But if it doesn't have such a requirement, then if the on-premise resources are not sufficient, we will set up something on the cloud, and I'll show you how fast and how efficient that is. Another thing to remember is that, of course, when a job comes in, the algorithms running here have to be aware of what the pricing is. We use spot market for the examples that I will show. So we utilize AWS monitoring to know actually how much it will cost us. So to set up a commercial cloud app, it's not done in the dark. It's part of what, let's say, the customer that submitted the job is willing to spend. So, moving forward. So the first use case we ran was for the CMS experiment, one of the experiments that discovered the Higgs boson. This is shown here. Oops. I think I was responsible for that, not... all right. So as you can see, we were able to deploy, these are 10% test, 25% test in less than a week. We were able to ramp up to 60,000 slots and run in preparation. So this was done in January and beginning of February. And that was done in preparation for a very important physics conference, the Morion conference, which was in March, where CMS was presenting results. So actually this use case contributed important physics results that were presented internationally and contributed to this experiment's physics program. And just to give you scale, when we did this use case and we ramped up to 60,000 cores, we provided through Fermilab, a partner with AWS, 25% of the total CMS Global Capacity. So that's significant. That is not just some elastic deployment for a couple of users and graduate students to do their analysis, but contributed significantly to the resources that the experiment used to do physics. So now we're done with high throughput computing, because most of this stuff did not really require, I mean, I guess depends how you define HPC. In my book, I define HPC as a tightly coupled calculation, where when I run, many thousand cores Each step of my calculation requires the involvement of all of them. So everything that I showed you before in my book is high throughput computing. But we have a lot of needs for true high performance computing. What I mean by that? We utilize machine learning for pattern recognition, and this should not be here. This certainly for training requires specialized high performance computing demands. So being able to stand up an HPC cluster at will is essential. Also, you don't want to buy this cluster because training, it doesn't happen very often. You do it, you forget about it. We do very large computations, tightly coupled computation at the petascale level of physics processes that are necessary for theoretical interpretations of the physics results that we obtain from these measurements. And again, here you do not want to have massive resources that you buy. You want to do these calculations a few times and pay for as much as you need them. Similarly, very large computations, tightly coupled, also at the petascale level, for modeling particle accelerators and detectors, which is very important both for designing new detectors and new accelerators and for analyzing the data that existing detectors and accelerators are producing, because that helps you understand the systematics. So I will finish here. I will also say that since Jeff belongs to the scientific computing part of AWS and you call your guys psychos, I'm actually the head of scientific computing division at Fermilab, and now I understand why my guys are giving me such a hard time. They must be all psychos. Okay, thank you. Any questions for me? Okay, there are questions. Okay.
I'll just talk really loud.
I'm loud too, so I can actually move from the microphone and we can have a dialogue and we'll be fine.
We just have to make sure it's recorded, sorry.
Oh, I come back then.
With the move to commercial services like this, do you see a decrease or just a change in the role of the leadership computing facilities at Argonne and Oak Ridge and other places?
So this is an interesting question. To me, HPC needs and on-demand HPC needs are agnostic. Wherever I can get this resource, I will use. So to me, when I say access to HPC, it could actually come from Argonne or from Oak Ridge or even from NERSC, which is not leadership, but it's... So then the question is easiness of use, security protocol, interface, availability. Certainly to get time on a leadership computing machine, you just have to put a proposal. It doesn't cost me a dime. It costs somebody a dime, but you know, I don't see it directly. So I don't see, so both play. I mean, the concept that we're developing, this kept cloud thing, it's to actually use at any given time what is most available, most cost effective, and most efficient. So it has a decision engine. So these resources play too. If it's very hard to get a workflow there, I won't do it. And if it makes sense to use Spot to buy something from AWS, I'll do it. If AWS prices jack up, I will not do that either. I will labor to go run to what is apparently free to me.
Any other questions?
Oops, another one. So stay to the microphone. This is our software for job submission I guess at the front end of Help Cloud. This is software that we have. It uses HD Condor, and if you are familiar with.
Another?
Depending on, first of all, I did not put petascale for machine learning because it varies. I can tell you with certainty that the simulations, either theory or detector and accelerator at the petascale level. So depending on the physics problem, different approaches are employed. So for example, when you look at neutrino detectors, I'll get too technical now. When you look at neutrino detectors, you use unsupervised learning because of the way the patterns sound and the way the noise is. And when you go to collider experiments, you actually don't use the signal to do your machine learning. You actually use pictures. Essentially, you try to teach the network how physics events look like. So it's like your usual, pattern recognition of, facial whatever, cats and dogs. The other thing is more like voice, so depending on which one you do, you take different approaches.
Got another one, good.
There will be no time for a demo. Maybe we should stop.
Let's do this last one.
No, I don't care, actually.
I wonder, so is the data directly going to the cloud to be processed there, or you have to move your data from your data centers to do the processing and then it comes back? And like, what's the price of?
We stage data in and we take data out. And I don't have the details on how much it cost me, but certainly we changed the way. So the way we were doing that when we were using on-premise resources was not the most cost-effective, that I know. So my guys had to devise new ways to do that in a fashion that's more optimal for the resources we use. As I told you, I'm the boss, so actually I don't really know the details. I do know that we have to spend within this week that it took us to ramp up. Part of what we did was also change the way we're staging data in and we're pulling data out. So clearly, that has an impact on cost, which commonsensically that's why you're asking me the question. And the answer is, for our workflows, we managed to get a solution that did not break the bank.
I think we're good. Let's take it at the end because I've got less than 10 minutes, and even though it's not a live demo. Yeah. Even though it's not a live demo, I still want to show a few of the slides. We'll skip that. Demo backups. Always have to have a backup. Let's show how to use Alsys Flight. So has anybody used anything in the marketplace? So you just go to the AWS marketplace, AWS, Amazon.com. That's our root URL for just about everything. aws.amazon.com/marketplace. Search for Alsys, ALCES. And you start up a cluster. It uses CloudFormation. And so it'll bring you to the CloudFormation page. And at the bottom, it automatically, since in this case, I'm using a cluster pre-templated by Alsys, it already comes loaded. I fill in a few parameter names. Let's see. Oh, I went too far. My stack name, boy, that's kind of tough to read. So everybody in the back, sorry, my apologies. But you enter the stack name, whatever you want to call the cluster. Do you want auto scaling? It'll automatically quasi-mount an S3 bucket. So if you have existing data, it's already mounted on the cluster. It uses Alsys tools automatically, so Alsys Gridware tools. But you can copy in and out of S3 very quickly. You also, at the bottom, you also give it the initial number of nodes that you want. Remember, it's auto-scaling. So you can start with 0. We call it 0-node clusters, which is kind of an oxymoron. But if you submit a job, it'll automatically spin up instances for you. You give the spot pricing that you want to use, the compute node instance type, and the key pair. So you have to have a key pair. And you're off to the races. You just wait. You got to do the login type. Max number of nodes. So you automatically, when you get an account at AWS, you have limits on your account for your safety. And you can also impose other limits if you want to. And you give it a CIDR block address. So that's how you're going to log into the cluster. And you can give it a username. By default, it's Alsys. You can make it anything you want. And it starts up. That's optional. Tagging is a great thing. I don't have time to talk about tagging. You review the stack configuration, and it's off to the races. So if you've used CloudFormation, you know what to look for in the console. It's going to spit out events. Hey, I'm starting up the security group, and I've done the routing. And you wait till the very end, and it gives you something like this. It gives you the IP address of the master node and the login name. So that's how you log into the cluster. Takes about 5 minutes. Just to give you a warning, if you go to try this, if you can't log into the master node right away, wait about 20 seconds and then log into the master node. Okay, sometimes there's a little bit of delay from when CloudFormation says it's ready from when you can actually get to it. This is the 2 bits of information you need to log in. So if you're going to log in, demo 2. If you're going to do it from Windows, good, bad, indifferent, you can use PuTTY. You input the IP address at the top. Then I like to, if you don't specifically enable keep alive, Putty will log you out of your instance. So I enable keep alive, and I tell it where the key is, and I browse to the key. That's it, IP and key. And I'm on the master node. I think the fastest, and one of my comrades in Psycho is here, I think the fastest I've ever done it is 6 minutes to the console. It may, if you're starting up compute nodes, it may take a couple of minutes, but they come up very, very fast. And you don't need a password. Everything is passwordless. Here's a key thing. You have root access to the cluster. If you're a bioinformatics person or a geneticist, you're doing this right now because that's one of the problems. You want an application installed on a cluster like one of the national clusters. It's going to take a while, and it's going to have to go through a process. You control the cluster. You can do whatever you want, install applications. You have root access. That's one of the great features of clusters in the cloud. Let's see. I can do things, it's really hard to see in the back, but it's SGE, so I can do a command called qhost. Tells me what nodes I have. It's got PDSH, a parallel shell built in, and I can look at what's going on across the cluster. And it also uses environment modules. So at boot, you've got a set of environment modules. So this is, if you're not familiar with it, we can talk about it offline. But it allows you to do things like you install an application like R. It'll give you the environment modules for R, and you can go off to the races. And that's, I got about 4 minutes left. So I want to jump back about 1,000 slides. Plan B is okay, except when it's kind of a pain in the neck. Any questions while I'm surfing backwards? Yes? So the question is about data in level 5, level 6 classified clouds. Actually, I have to apologize. I'm more on the public side. I don't work with that side of the AWS business, but I can connect you with someone who does. But in the normal public cloud of AWS, you can encrypt your data using your keys, using our keys, or we can store the keys for you. You can encrypt it before you upload it, so you're in control of your data. And also, we never move the data from whatever region you put it in. It's always going to stay there, so we're not going to take your classified data on the B-21 and put it in China, for example. That will never happen. You have to do that. No, yeah, you can't put classified data on a public cloud. Well, you can, but, yeah, you're going to make small rocks out of big rocks. Yeah. Let's see. Any other questions real quick? I just want to do a quick summary. Boy, howdy. I got a lot of demo slides. I apologize. I wish I could have done this for you in real time, but I kept getting dropped off the net. And one quick point, I talked about two things I want to back up on. The use of job schedulers in the cloud. Since there's so many cloud resources, sorry, karaoke voice. You don't have to have a shared cluster anymore. Each researcher can have their own cloud or multiple clouds. Or clusters, excuse me, I kept saying cloud. Clusters. Also, your cluster doesn't have to be the traditional model with compute nodes and a master node. It can be more like a MapReduce or a Hadoop or Spark architecture. So I hate to say it, I have some friends at Oak Ridge, but if I went to them and said, hey, can you reconfigure Titan for Hadoop? They'll kill me, even though they're good friends. But with the cloud, you can reconfigure on the fly. It's just code. You don't have to redo any cabling. And the use of the job scheduler is great in the cloud for one good reason, job dependencies. Finish this job, then run this job, and then run this job, or what we call job arrays. If you're going to run like a Monte Carlo simulation and you want to run 100,000 jobs at the same time, you can use job arrays. So they're very, very good for the cloud in that regard. However, you don't necessarily need them because schedulers are designed to share resources, but now with the cloud, you have the ability to have your own cluster. I always thought that was pretty cool. It's very easy to recreate clusters in the cloud. So this is one of the reasons people are going to Docker and going to images basically is what it is so that they can reproduce results if they need to. You can do the same thing with cloud. It's just code. So this is my cluster, here's my code, and here's the output. You can save that and rerun it at any time you want. Or we also have ECS available at AWS, Elastic Container Service. Boy, I'm terrible with acronyms. Spot, think about Spot. The combination of Spot and HPC is a wonderful thing. I can give you examples of what people have done using the spot market and how much money they've saved. Dr. Spiros talked to us about what Fermilab is doing and how they're taking advantage of the cloud for cost-effective computations when they need it. And you saw the peaks and valleys. If you didn't look too closely, there's some great big, huge peaks and valleys. I can't think of any place else but the cloud where if you need 60,000 cores, you can get them in an hour. And if you're done with them. If you want to order 60,000 cores, I'll see you next year, right? Alsys Flight is a great place to get started with HPC in the cloud. Easy, it's got a lot of applications. There's great documentation. You can do visualization with it. And this is only the beginning. Once you get used to HPC in the cloud, you can now start to think of how can I take advantage of the cloud with my applications and rethink how to rewrite them. There are people doing it right now. I can tell you that there's some areas of the US government that are rewriting classic serial applications or MPI applications to take advantage of different services on AWS. For example, Lambda, ECS, and continue to use EC2 and SQS. So there's lots of ways to adapt to the cloud, but the easiest way is to start using Alsys Flight in the marketplace. So thank you very much. I appreciate everyone's attention. Everyone stayed. This is great. Thank you very much. Oh, by the way, I have a whole bunch of business cards here if you want to grab them. I'm going to be in the Psycho booth at the exhibition if you want to come talk.